Welcome to our regular monthly meeting of the Renew Sydney Central Branch. We're meeting here in Ashfield, which is in the land of the Gadigal and Wongal people of the Eora Nation, and we acknowledge elders past, present and emerging, and their crucial understanding of how this land operates, and there's so much we can learn from them. Tonight, we've got a very special speaker to come and talk to us, Dick Clarke. He's president of Renew. He's been involved with the Renew for a long time, but he's also done so much more. He's a very well-renowned sustainable building designer. He's been at the forefront of sustainable building design for as long as I can remember. His firm's done an amazing amount of work and always being at the cutting edge. Now they're doing a lot of work with Passive House. But Dick's also done a lot in terms of sharing his knowledge and being involved with the industry. I first met Dick when I joined ABSA, and he was president of the ABSA, which is the Energy Assessors Association. That's 20 years ago now. But I've met him in other venues at a basics consultation group. He was a driving force behind the Your Home document, if you're familiar with that, which is like the Bible for sustainable design in Australia. I had a small part in helping with the most recent edition of that, but Dick has been involved all the way through with that document. And last year, he was recognised by the Building Designers Association, who gave him the Lifetime Achievement Award. So it's a real honour to have Dick here and to talk about such a crucial issue, building resilience. Every week or so, we get hammered with the extremes of climate, and it's only going to get worse. And we need to really put on our thinking caps on how we need to deal with that. So I'll hand over to Dick.
Thank you, Graham. Thank you for that introduction. It makes me sound much more important than I really am. The Lifetime Achievement Award was actually from Architecture and Design magazine for the Sustainability Awards, but it worried me at the time because I thought, well, you've got to be kind of either really, really old or very nearly dead, surely, to get a Lifetime Achievement Award. And I didn't know whether that boded ill for my future or not. Anyway, so tonight, we're going to talk about resilience, which, on the face of it, seems really boring, but resilience is actually, it's about life and death ultimately. But before you get to that kind of ultimate stage of needing to be resilient in whatever sphere you find yourself, there's the stage of being able to just cope. And so really, resilience in buildings is about just being able to have a building that works for you and that enables you to basically take the event, whatever it is, in your stride and get on with life. We're talking about disasters, but also extremes, and then I guess the slightly less dramatic but equally inconvenient blackouts and shortages of mains water and so on. And I guess, kids' birthday parties can be difficult to live with as well. See how we go with that one. So extreme weather, it's definitely impacting us. Just last weekend, we saw floods in Sydney. We've seen floods in other parts of Australia that have been much, much more disastrous and really quite life-threatening, going back, many years now. Bushfires are a regular and will be an increasingly unfortunate regular occurrence that we have to deal with. And with all of that, the extremes obviously affect the major utility infrastructures, most obviously in terms of power, but also in terms of water and to a lesser extent, sewage and so on. So homes can be built to cope with these things. So let's have a look at how that might pan out, some of the specifics of it. We have a thing called the Resilient Building Council, that are now focusing on that. They advise a large number of bodies, governments, and so on, and they've got some really useful resources. And the last slide in this deck, which will be made available in the chat, includes links to some of their documents. So resilient homes can reduce inconvenience. That's the kind of, first step. Oh, there's a blackout. Oh, my fridge is still running. Isn't that nice? That's more than just nice. It means your food's not going off. So that's reducing wastage, and that's a sustainability plus. They also save money in the long term, and to an increase, a very small trend, but an increasing trend, reducing insurance premiums. And there is yet to be more work to be done there to ensure that, that was the wrong choice of words, wasn't it? To enable insurers to understand what a resilient home is, so that they will then say, oh, okay, then, we will reduce your premium because you're much less likely to be damaged by whatever event you're preparing your resilience against. It also means that the home is more versatile in the long term in terms of changing conditions, and then you can live through and recover more quickly from those extreme events. So resilience is more than just surviving the extremes. It's taking them in our stride. Now, I kind of semi-retired from full-time building design work last year, and one of the things I've enjoyed most is, that's not my boat. That's my boat. I must have eaten too much sugar at Christmas last year, and decided I needed to buy an old wooden boat and electrify it and solarise it. So I bought this old boat that's a little bit older than I am, and took it back to deck level, built a new cabin, put solar panels on the roof, put an electric engine and some batteries, and now it's one of the most sustainable boats on Pittwater. Certainly in terms of motorboats, sailing boats, different story. And I could motor that, sail that to New Zealand, no problem. I could, set off and just away we go. And as long as conditions look like that for about 12 days, because I can motor all day on pure sunshine and just hove to at night and have a little snooze, and then sun's up next morning, away we go again. 12, 14 days, no worries. I'd beached Asbro, and I'd be eating the fish and chips and having a wonderful time. But the reality is that my boat would struggle in conditions like this, which happen regularly in the Tasman. And it would need to actually be resilient enough to cope with that, and this would overcome it completely. So, life isn't always like this. We need to be able to cope with that. So when we're dealing with our houses, we have to make them healthy and comfortable. They have to be durable, and durable without lots of maintenance input. So that's one of the key things as well. Because I don't know anybody who enjoys doing maintenance on their houses. Maybe they're out there somewhere, I don't know. They need to be energy efficient, because that reduces the demand on your energy side. Use a low embodied carbon. It's not such a direct input into the resilience, but it's just a really good thing to do. And therefore, they need to draw on passive design elements to get that kind of ability to take things in their stride. Affordable utilities and bills, because part of resilience is that you might find external forces raise bills for whatever reason significantly, coincide with perhaps your inability to pay for them because your income might be stonkered by some event or other. So the better you can look after your income, yeah, that's great. That can be out of your control. But if you can bring your utility bills down, that increases your economic resilience and resilience to the extreme events, obviously. So what are they? Heat waves, cold snaps, bushfires, floods, power outages, and mains water outages. If we were in other parts of the world, on that list, I would have to put earthquakes. But at least in this part of Australia, earthquakes are very infrequent, and they're usually very mild when they happen. So what can we do to actually respond to some of those things? So building design and specification obviously has a big impact on our response to heat waves and cold snaps. Likewise to bushfires and floods. But floods also affected by town planning. So if if you're building in a floodplain, should we be building in a floodplain, I guess is the question we need to ask. So there are some things there that are outside of our control. If you're already living in a floodplain, then there are things we definitely need to do that elevate that aspect of resilience dramatically. And then mains, water and power outages, that's about building systems and how we set those up. So the one thing that we probably can't talk about and do anything about is the town planning issue right here and now. We can certainly support governments that say don't build on floodplains, but let's move on to what we can talk about. So in terms of retrofitting, passive design, yes, you can retrofit passive design to uplift whatever potential a building has. If it's a new build, obviously a blank sheet of paper, there's no excuse for not getting it absolutely right. But we can always do things to existing buildings to improve their thermal comfort. Active design, so that's about your appliances and energy systems and so on in the autonomous systems. And we have, at Renew, we've been working, as you would know, on the Getting Off Gas Toolkit, which is incredibly useful and needs to get out there into the wider world big time. So let's have a look at these extreme events and what we can do about them. Heat waves and cold snaps, I'm going to run them together because whatever you do generally to improve the thermal comfort of your building and the thermal performance will work if it's done with passive design principles. It will work for both extreme events. Extreme heat we know about, and we don't in Sydney thankfully see much of that, but that was down the road from my sister-in-law's place on Lake Geneva back in 2012, and that's her fair income photo. So surviving heat waves and cold snaps, it's good thermal performance of the building envelope plus some auxiliary heating and cooling systems that have an independent power supply. So if we're looking at thermal performance, passive design, look, I'm a semi-retired, I don't like that word, I'm a building designer who's had a change of job description because now Renew keeps me and Graham really, really busy, So a little bit of work, a lot of Renew, it's all a big party, we love it. However, I'm not an educator, okay? Yes, I've done a lot of training with the industry, but I'm not a trained educator. People who are tell me that if you want people to remember something, give them 5 points because there's 5 fingers. Now, that seems a bit simplistic to me, but I'll take their word for it. The problem is that passive design doesn't properly fit into 5. I know there are people who theorise it this way, but I don't agree. So we need to basically, grow a 6th finger, if you like, to help us remember. So first one is orientation. Which way does the building face? So that's all about the topography and your locality and so on. Number 1 is about zoning of the floor plan. So there's not the zoning the building sits in terms of the council zoning. This is about being able to zone off or control areas within the building. So it's not just open plan gone mad. Third one is thermal mass. So that's just a kind of a battery for warmth and coolth. Fourth one is shading, self-evident. Fifth one is insulation, and that is the whole building envelope, floor, walls, windows, roof, the lot. And then the 6th one is ventilation, the ability of the building to provide fresh air, but also breathe out when things are really hot. And that's fine. It's basically got 2 main functions, and there's a couple of extra fingers there, and you'll see why in a minute. But preheating by solar energy is the obvious thing for winter, and then passive cooling comes from it comes from excluding the solar gain. So bring the sun in winter, keep it out in summer with those other aspects together, and you can make it work. But it's always occurred to me that there's something missing. And if you use the 6 key element theory, and that's glazing. Now, it's a little bit different in character to the others in that it is a kind of a specific building element, whereas the others are kind of more design principles. But when you put it with the others, you can see that with the exception of zoning of the floor plan, there is a direct relationship between the glazing and how each one of those other things works. So the orientation, where's north? If you don't have glazing on the north, it doesn't matter. You've wasted your time, you know. Insulation, glazing forms part of the necessary insulation barrier to get control of heat flows, etc. So we'll go through these in detail. Now, I've put a lot of technical kind of low-grade technical slides. So they're not scary technical, but they're, you know, not just words and pictures. A lot of diagrams into this presentation. I'm not going to talk to every one of them because we will be here all night, but they're all in a PDF and it will be available for download on the way through. So fundamentally, you know, orientation, we know that the Earth has a tilted axis, and as it goes around the axis, as it goes around the sun, that's what gives us the seasons. Bit of a relationship with the moon going on there as well, and that's what over 3.4 billion years has created life on Earth as we know it. And so we have the low angle winter sun, high angle summer sun. We can use fixed shading or active shading to keep that out or bring it in when we want it. In terms of zoning spaces, on the left is the first floor and on the right is the ground floor of a project home floor plan with no potential for zoning off spaces within or between the levels. So if you want to cool that house, you cool the whole house. You want to heat the house, you heat the whole house. You want to shut the kids up, you've got to kick them outside because you cannot isolate acoustically even any one part of the house except for the bedrooms. Mad, open plan, gone mad. And this is then about zoning between levels, that you might have a really good level, a good plan that enables you to close it off, but there are also times when you might want to open it so you get stacked ventilation going through. So it's about control. Thermal mass, as I said, it's this warmth and coolth battery. We can do hybrid buildings that have a lot of thermal mass on the inside. Brick veneer is a hybrid construction, but the thermal mass is all in the wrong place. It's all outside, subject to the outside elements, and then we have to insulate against it. So reverse brick veneer is as much smarter thing to do. It's never taken off. Bunch of materials with their different volumetric heat capacity. Great barbecue conversation stoppers to discuss the volumetric heat capacity of water versus air, etc., and so forth. And then there's some diagrams about using shading both externally and internally to regulate thermal control. Little diagram about the way structures respond to temperature changes. The big black line is a high thermal mass building. And this is all very theoretical, of course, but it's generally true. So the fixed, when it comes to shading, the fixed elements, things like the eaves, awnings, even fences, external blinds and trellises, and they can be trees and vines, and those, some of those things you would have no control over because they'll either be beautiful and you don't want to chop a tree down, or they're on the neighbour's side or whatever it might be. But basically, it's north-facing facades that need to accentuate that change in the seasons. East and west, it's just about keeping the sun out pretty much the whole year. So another diagram reinforcing the same thing. And also then to think about reflected heat and the kinds of things that the plants can do for you with soft landscaping and so on. And this is a little movie about active shading. Now these are hybrid, so they're a bushfire shutter as well as big shade shutters. And I know I'm not going to get any prizes for the cinematography on this, but I was on top of an 8-foot wobbly stepladder. So it's a technique I don't think Hollywood's going to pick up on. But you can see from that it gives you lots of control over where you get the shading. Each awning is individually controlled just on winches. And when they're down, you get the bushfire shading as well, bushfire protection. And then you can have these awnings, if you're not in a bushfire zone, that are made of fabric that slide in and out. I love that contrast. So then it brings to the fifth element of that, which is the insulation. That's just about stopping heat from flowing through the non-glazing elements of the building. But this is where it comes back to my seventh element, that the glazing is part of the insulation. Now, some years ago, and I don't know how many years ago it was, I wish I was part of the discussion when this happened, the powers that be decided that when we're talking about walls and roofs and floors and so on, we would talk about R values as a resistance to heat flow. And when it came to glass, we'd flip that and talk about conductivity. No idea. The idea has no merit in my view. I mean, I've tried to understand why they would have made that decision. The only thing I can come up with is that if you talk about R value in glazing, you're talking about really small numbers. Well, single glaze anyway, really small numbers, and that made them look bad. So that's the only thing I can come up with as to why they went that way. Thankfully, arithmetically, they're just the inverse of each other. So if you look at the U value of a window, and U is the symbol for conductivity in this case, just flip it. 1 on U gives you the R value, and that's why when you compare it with say an R6 or R5 bat in the ceiling, and then you get a piece of glass and it's 0.2 maybe, you realise just how bad glass is. And this is where the rubber meets the road. That 10 square metres of an uninsulated brick veneer, an insulated brick veneer wall compared to an uninsulated single glazed window is 10 times more powerful as a piece of insulation. And that's just brick veneer, which is, not very special. So then when it comes to thermal mass and insulation, this is about lag time and the ability to absorb and redistribute thermal energy. So, sun's got to get the free solar heating has got to get into the material, whether it's bricks on a wall or a concrete floor or a phase change medium in behind a plasterboard wall, if you're really, kind of doing something a bit interesting. But it absorbs that energy, it stores it, and then when the ambient temperature around it drops, it re-radiates it. And this is just some of the time lags per thickness of different materials. So I'm not going to dwell on that. This, however, is quite an instructive slide with the images there of the thermal imaging done to show where the heat goes. And you can buy little FLIR add-ons for smartphones now. FLIR cameras used to be like $3,000, and now for a couple of $100 you can buy a little FLIR thing that clips on the front of your iPhone or your Android, and you can wander around your house and take photos and find out if they really did fit the insulation where they said they did. This one is really interesting as well. So some years ago, Newcastle Uni did some research. They built 7 little buildings, and they were all identical in plan size and roof shape and so on, but they put different materials, different constructions to see how they all worked. And what they discovered was that roofing material is less important than colour, and colour is less important than insulation. And that kind of challenged a few of us who went, no, you've got to have metal roofs and they've got to be light colour. Yes, they work best at blocking heat, but the big thing was just having insulation underneath. That was approximately 12 times more effective than worrying about roof colour. Now, Think Brick, which is the brick manufacturers association, have just thrown some money at the uni to upgrade. In fact, it's been done. All of those buildings have now been upgraded to the National Construction Code 7-star, which is the current standard, which Renew fought long and hard, and our policy manager, Rob McLeod, rounded up 105 organisations to, at last, after years of obfuscation by various other building industry bodies who shall remain nameless. We rounded up 105 organisations to finally become the loudest voice in the room and convince the government to take this big, bold step of going to 7-star, even though 7-star is still inadequate. But it's something. So now they're going to run a whole lot more tests on different things to see how it works in 7-star. So that'll be interesting. Insulation also has a direct effect on condensation. Oh, I forgot to start my timer. Sorry about that, folks. But anyway, so yeah, condensation. So this is a big one because resilience, we're seeing a lot of press about people in the, the housing crisis being charged $800, well, one in the Herald today or Guardian, $825 a week for a rat-infested mould, I can't remember the word they used, but basically, uninhabitable, totally mouldy building. And so that is not a resilient building. Mould is extremely hazardous to human health. So we need to get control of mould. The insulation and the kind of insulation materials we use is critical for doing that. And so if we look at the thermal profile of an uninsulated brick veneer wall, and dew point in this case is at 15 degrees, that's the point at which water vapour will condense into liquid and therefore induce mould. The amount of time that it takes to get through the temperature to get through that wall is quite short. Now, this is a bit technical and I'm not going to dwell on it because, this is a 15-minute discussion right on these two slides. But compare the two. As soon as you go to an R2 insulation, the amount of time it takes for the temperature to transfer through that wall is stretched dramatically. And it doesn't necessarily fully solve the problem because you've still got to look at ventilation and how you're handling indoor air quality and so on. But it's the first line of defence, if you will, against mould. There's a neat little calculator on the web called the dew point calculator, dpcalc.org, and you can put in your temperature and humidity and it'll tell you what the dew point will be. So if you're getting get on the bomb or listen to the weather forecast for the temperature and the relative humidity, stick it into this and it'll tell you what the dew point is. And it is surprisingly high. And that means that condensation will form, in this case, 20 degrees, 85% humidity. So this is like the day after an autumn rain event, such as we've just had. The dew point's 18 degrees. Doesn't take much overnight to bring the temperature of building materials down below 18 degrees. Condensation will form on those materials. Point 6, or key element 6, is about ventilation. In a lot of buildings, especially older ones, it's uncontrolled and we need to get control of that. We want ventilation, but we want to know where and when it's happening and that it's happening in the right ways. Cross ventilation is important. That's a good floor plan. You can imagine any kind of bad floor plan that wouldn't allow it. And also then think about the kind of windows that we have that will encourage good breezes to come in. So these ones are all casement windows facing northeast because that's where the sea breeze hits Sydney. Anything from the northwest, who wants it? So, even if the windows are left open in a hot nor'wester, it's not going to scoop them in if they left home without closing the windows on a hot summer day. Ceiling fans are also part of this because the ceiling fans are an incredibly powerful low energy tool for giving us thermal comfort in hot weather. And if you couple your ceiling fans with your air conditioning, you will get a fourfold increase in the efficacy. Isn't that a wonderful word? I love efficacy. So fourfold increase in the efficacy of your aircon. So if I was dictator instead of Dick Clarke, boom, I would mandate that if you've got aircon, you've got to have ceiling fans and that they need to be coupled together so that they're idiot proof. And so when we do new buildings, and sometimes it's possible in a retrofit, but not always, we will make the aircon slave to the ceiling fans. This is in a public building, so we needed explainers on the wall so that when people walked up to turn the aircon on, they understood why it wasn't working because the ceiling fans weren't working. So it's a little explainer. So that brings us all to element 7, the glazing. It's the Achilles heel of buildings if it's not done the right way. So it's obviously, it's got to be there to get the passive solar heating working, but it's also got to be in the right places, shaded the right way, insulated the right way for passive cooling to work. So a couple of pie charts there about where it goes, just a quick reminder of that one. So when we come to specifying and designing glass, don't stick your head in the sand and just go, oh, it's all too hard, or the blokes at Steg Bar said X, Y, and Z or whatever. It's got to be appropriate. It's got to be thought through really well for it to work properly. Now, I'm going to race through a bunch of slides here that'll all be in the PDF that show the kind of relationship between radiant heat and reflected heat. But just a quick pause on this one. I'm going to step out of frame here for a minute, people on the Zoom, or maybe, I can use my little pink dot, which you guys can't see. But what I'm looking at is the top left example here, which has a thing called clear SHGC 0.86. Now, SHGC is simply solar heat gain coefficient, and it's a number between 0 and 1. So 1 is 100% of the solar heat gain goes through, 0 would be none. So 0.86, so this clear glass, which is your typical single glazing, lets through 86% of the solar heat gain. If we then go down to double glazed clear, down on the bottom right, the SHGC only drops to 0.77. So most of the solar heat gain is still getting through, but the radiant heat is not. So there's a bit of a misconception still out there in the building industry that double glazing stops radiant heat. Oh, I don't need to worry about shading on the west because I've got double glazing. All you're going to do is make an even more powerful greenhouse. So moving right along, another little diagram there. And then this table gives you a clearer comparison of the kind of performance numbers that you'll get. So the U value, we talked about that, that's the insulation or conductivity, in fact. So put 1 over 5.8 and you can see it's not a very big number. The solar heat gain then is also affected. And so this is where if you can't get shading on the west because you're too close to a boundary or whatever it might be, then you can use toned glass and other special glasses that will reduce the solar heat gain. But there's no substitute for double glazing for reducing conducted heat flows. There are things called WERS ratings on windows, which is the window energy rating. Now, they're not perfect, but I guess it could be WERS. And I just to sort of step back from the technicalities and think about strategy here for a second. The earlier you make decisions, the better value they are. The more you will get out of a decision if it's made early on, rather than trying to do a catch-up at the end. So it's always best to get things sorted out at concept stage than to have to retrofit them later down the track. Now, that's all very well and good, but if you've got an existing building, you're already halfway through that process down the bottom there, and it is what it is. It's still worth renovating buildings. So I would never subscribe to the view that all old buildings should be knocked down and start again with all of them. No. Most older buildings have got a lot to offer in terms of the materials are already paid for. They're already there. The carbon that they've emitted in manufacture has, been dealt with. And quite often they've got great character and there are lovely things about them that you want to keep. But so it's actually quite, I think, relatively easy to improve the thermal performance of older buildings without trashing them. Graham mentioned the Your Home manual before. It is, I do feel like it's a bit of a baby of mine because I was at the very first, is this a good idea meeting that was held by the Australian Greenhouse Office back in 2000 and something, 1 or 2 maybe. And now we're on edition 6. So that's always a great reference source. And that takes us then, I guess, to the ultimate in terms of what we can currently do in building performance, which is the passive house standard. And it is certainly the best option for surviving the extremes, smoke and dust, and high humidity because of the internal system. So I'm going to play a little video.
Passive house explained in 90 seconds. Does your house have a heater in the basement or maybe a fireplace? Probably also a central air conditioner or maybe a window unit. Did you ever wonder if it was necessary? In 1991, a physicist in Austria, Dr. Feist, built the first passive house. Here's what he did. 1. proper insulation. It's just like wearing the right winter jacket, it also doesn't need a heater. 2. No air leakages. There should be no holes, small or large, to let hot air out of the house. 3. No thermal bridges. A thermal bridge is like a road for heating energy in which warmth can travel right through your walls. As a matter of fact, most of our houses have thermal highways in our walls where heat can easily travel to the outside. Plus, the house needs proper windows most of the time with triple pane glass. It needs to be oriented properly so the sun can heat it in the winter and shade is provided in the summer. And it uses an HRV, a device that provides the inside with fresh air without letting the heat out. Add all these things up, and it turns out your house doesn't need a heater or air conditioner. So where does the heat come from? A passive house needs 90% less energy, and that can easily be supplied by your body heat, the sun, your appliances, light bulbs, and even your TV. This saves you a lot of money on your heating bill and helps preserve the environment. Did we make it in 90 seconds? You bet we did.
So insulated, efficient, comfortable, ventilated. Now the ventilation bit is quite critical, but basically, the passive house standard, it's verifiable because we do a blower door test to check the air leakage, and that's a kind of a proxy for how well everything else has been built or not. If it fails the blower door test, you basically go around and fix things until it passes. To get the standard to be certified, it has to have less than 0.6 of an air change per hour at 50 pascals. 50 pascals is like a 15-kilometre-an-hour breeze. So it's not a gale, but it's not nothing. Now, the critical thing in terms of resilience for us is really about the heat recovery ventilation system being able to be filtered, because it can take out every perceptible bit of bushfire smoke. So they can filter down to PM 2.5. So somebody in Canberra has done this during a bushfire event. Outside was, like visibility 200 metres, 300 metres in the smoke. And they were measuring their indoor air quality particulate. Now, he said that he couldn't smell smoke. It still registered a very, very small amount. I think it was about 3.5% of the 100% that was outside. So that's an extraordinary kind of result. And bushfire smoke is not good for you. No smoke is really good for you. Now, the bright kind of thing going on here is that you don't have to build a new house. You can use what they have as a kind of hit list, the renovation hit list called NOFIT. And basically, you do as many things as you practically can on that list, and you can still get a kind of certification for it. But it's just common sense stuff, like the stuff we looked at, but just always done without compromise. And that gives a very, very good result. So once again, it's this point where you make the decision will get you the best value out of it. So what's a passive house look like? This is just a few photos of the Thornley house, which was Sydney's first and Australia's second, being constructed. And to this point you go, oh yeah, this looks like a house, doesn't it? And then the airtight wrap went on. So that's airtight. The ceiling panels are sealed to it. So the ceiling panels are also airtight, floors airtight. Windows and doors go in, they're taped to it, so they become airtight. And then all of the insulation goes in, and then the blower door test is done. And once it passes that, then you put the skin on, you put your services in and internal fix out and so on, and voila, you have a finished passive house. What do they look like? They can look like anything. So passive houses is not a determinant of style or design in that sense. They can look like anything you want. So extreme heat. PV can run air conditioning during the day. That it can do that at no cost. That's because the solar output period in the peak of the day is aligned with your need for air conditioning. But if that air conditioning is needed to run into the evening to keep you comfortable, then, and there is no mains power, I guess I'm talking about here, and you have a PV system which is disconnected from the grid, and it's probably worth pointing out that The standard PV system is slave to the grid. So if the grid goes down, your PV system shuts down as well. And that's so that you don't become a power island. So when, what was his name that did the linesman? American country singer, Glenn Campbell. Yeah, what was the name of the song? Who was the linesman? The Wichita linesman, that's right. So when the Wichita linesman comes around, he doesn't get zapped, because then they never would have been able to write the song. So that's why it shuts down. But you can have it set up so that it disconnects you from the grid, but still allows your internal systems to run. And that makes most sense because, you got a PV system you paid thousands of dollars for and you can't use it. That makes no sense. So a battery may well make sense to allow you to offset your demand from your production period. Okay, bushfires. First thing to work out is what your bell rating is. Is anyone here in a bushfire zone? No one in the room? There'll probably be people on the Zoom who are. You need to understand what your bushfire attack level, the bell rating is. Basically, if you're in bell 12, the first one is bell low, that means do nothing. Bell 12.5, you've got to survive ember showers, low level radiant heat. And so the external materials have to be resistant to ignition, but hardwood's okay. And you can't have gaps anywhere in the building perimeter of more than 3 millimetres. They have to be less than 3. The next level up is bell 19. It's heavier ember showers, radiant heat exposure up to 19 kilowatts per square metre at 50 metres. So that's what the 19 signifies. It's got to be able to survive flying, burning debris, and the external materials have to be resistant to ignition. So some hardwoods are okay. Once again, no gaps. Bell 29, next level up, heavier ember showers again, radiant heat to 29 kilowatts per square metre, more flying debris, etc. So similar to 19. Then bell 40 is a bit of a step up. So even heavier ember attack, radiant heat exposure to 40 kilowatts, flying, burning debris, possible flame contact. So no external timber, no gaps more than 3 millimetres, and much tougher glazing specifications, including rubber seals and so on, have to be capable of surviving that. And then bell flame zone, this is the one that's really quite problematic in many instances. It assumes a deluge of embers, radiant heat beyond 40 kilowatts, flying debris, flame contact for up to 10 minutes plus. So obviously no external timber, nothing combustible outside, no gaps, and shutters on windows unless they are FZ rated windows, and they do exist, but they're very expensive. Shutters aren't cheap either, and the shutters have to pass certain tests and so on. So flame zone is difficult. And once again, just a reminder of that system there we used. Now, a reminder again about the usefulness of HRVs. So even if you're not building a passive house, if you get your building airtight, and this is in no matter what bushfire rating you've got, if you get your building airtight and you fit an HRV that's got the filtering capacity, you can change filter cartridges. So you can pull a cartridge right out and run unfiltered if you've got nice clean air most of the time. But if you run a PM10 filter, which is what most people seem to do, when you're in a heavy bushfire smoke situation, you can pull that cartridge out, stick in a PM2.5 and get, almost literally clean air. And then when the bushfire's gone, you can pull your PM2.5 out, put your 10 back, so that you're not using expensive filters all the time. And the PV and battery, just to make sure that the batteries are installed away from embers and flame, obviously, because while they won't explode of their own accord, you're listening, YouTube, they will suffer and could explode or catch fire if they're exposed to direct flame from an outside source. So when it comes to flood resilience, I guess, look, the things we need to look at are wet proofing the building, making things able to be dried, thinking about elevation, landscaping, how does that direct water, And then the design guides that are published are really useful as well. So that's just a photo of Saturday morning last weekend around Narrabeen, and a little diagram that Lismore City Council put up after the event, which was nice, and the flood mapping of the Hawkesbury Nepean Basin for Western Sydney on the right, and on the bottom one, it's the flood mapping for the Sydenham Bankstown area. So basically, the authorities know these floods are going to happen, and they could have mapped exactly where and how they're going to impact. So there's another useful thing that the government is currently running as a voluntary kind of house raising scheme. I don't think it's going to affect anyone in Sydney terribly much, but they're certainly pushing it up on the North Coast. But what we can, if you know you've got flood issues, you can, even by retrofit, you can kind of dry proof the structure by getting the absorbent materials up above the flood level. Now, flood levels are published as the PMF, probable maximum flood level, which is quite high, and you'd normally then have a margin of safety above that again, and that is all well above where people will tell you it's flooded over X number of years, and that's because anticipating climate change and the severity of events getting worse, and so there's a margin of future proofing. Another way of doing it is to make the house float, where you basically build it like a marina pontoon with columns that are in the marina industry called dolphins. I have no idea why. And so this is a big reinforced concrete flotation base. And when the floodwaters come, it rises up around the dolphins. The dolphins keep it in place. And you swap your car space for your dinghy, your tinny space. And yes, it is entirely practical and possible. This is some modelling we did about 10 years ago. And you can have flexible service connections that, and that's all off-the-shelf technology and fittings. That's easy to do. Lake Macquarie City Council have actually written it into their DCP. Electrical equipment, especially expensive electric high voltage equipment, is well above flood level. Now, power outages, this one's kind of a no-brainer, PV, battery, away we go, as long as it's the isolated type away from the, to disconnect you from the grid. So Mains Water reaches, it really gets back to the whole kind of water sustainability thing. And in Sydney, at least, it's been a while since we've had a drought. But people in other parts of the country have been going through some pretty dry times. And then, when they're enjoying wetter years, we've been in drought. So we know these things are cyclical. We know they're going to come again. We're pretty sure they're going to get worse. Whether they get longer, we don't know. Whether they get more severe is almost certain. So the severity of a drought is measured in both its duration relative to the amount of rainfall that's been had, but also just the amount of rainfall. So if we had no rain for 6 months, we're in drought. But we could have a drought that's kind of 2 years long, but we've had, just below average rainfall and we're still in drought. So it's kind of a dynamic thing. So the other thing that can happen, of course, is that water mains burst without warning. They never know when that's going to happen. And they also will had scheduled maintenance. And while that's usually notified, it's still an inconvenience. So surviving without mains water, tanks and so on, gutters, and you need a bit of rainfall in the first instance to make it happen. So rainwater safety is something to consider. It's all about location. So what's your local air quality? If you're on a main road or you're under a flight path, you're going to have airborne particulates coming down onto your roof. If you've got lots of overhanging trees, you're going to have leaves coming down onto your roof. Those things are not good for rainwater quality if you're going to use it for anything other than watering the garden or flushing a toilet. So the first thing is to look at gutter filters to filter out the nuts and bolts as they fall, and then to look at a tank inlet filter. Now, I'm going to be a bit controversial at this point, because up on the top right there you can see looks like a wheel. It's not. It's one of those round inlet filters with gauze on the top. and the downpipe enters into the top of it, or sits on top of it, and as the leaves and detritus falls, that catches big stuff, as in not sediment, and you get up on top of your tank and you pull that out and you empty it and you put it back in your tank. Okay, simple, very effective. Below that is what's called a first flush device, and this is mandated in New South Wales. New South Wales Health and every council will mandate that if you're putting rainwater on, you have a first flush device. I say it's folly, because unless you do a very detailed hydrological study of your roof areas, the length of your gutters, you don't know whether that's catching and diverting too much or too little. And so this is just a standard thing that gets fitted onto the side of every rainwater tank, and is how effective? Who knows? So if we don't know how effective it is, and yet we're assuming it's protecting us from bird poo and who knows what else, I think that's foolish. So I would always suggest that you don't fit those, or if they are fitted, that you plug them up and drain them every now and then, because they will catch a certain amount of sediment that comes through. But the other problem with them is they're all supposed to have this little slow drain so they're always ready for the next rainfall. We often get rain that comes in intermittent showers, but small amounts in each shower. If that first flush device is capturing every one of those showers and then dumping it for half an hour, and then half an hour later you get another 5-minute shower and it dumps that too, you'll get no water into your tank at all. So it's another reason why I think they're a bad idea. That's my personal professional advice. It is not the regulation. So they are required by regulation, but I would suggest it is a much safer thing to do to have proper filtering on the outlet of your tank. These are big filters, once again, that take out sediment. And then anywhere you're drinking the water, you run it through an activated carbon filter. And that then gives you really nice, clean, pure water. So 2 things to think about: how's the water going to get used, and what's my location like in terms of the air quality. In terms of tank size and so on, I mean, look, you can have an outdoor tank with a tap on it and you put your kettle under it if you want to. That would be a small tank, I would assume. And then depending on how much space you've got, you work up to bigger and bigger tanks. And those tanks are going to be constrained by space, by the connectability to existing buildings and so on. So lots of constraints, but I think it's always best to just go for the most that you can possibly store and capture. So as many downpipes as you can get into that tank, and make that tank as big as you practically can. And that gives you the most reliable resilience. Now, at this point, I've gone pretty quick. Yep, I'm guessing I'm probably right on about time, and it's probably time, therefore, to tackle the one that I really cannot resolve. I have no idea. So you can take a screenshot of that if you want, and if you're at home on your Zoom, I think Command Option 4 or whatever it might be on your computer will take a screenshot, but that is also going to be on the chat. You can do a copy and paste, and it is the last slide in the PDF deck. And so there are some very, very useful links there. And with that, I will say thank you very much. Oh, you want me to stay? Oh.
Yeah, thanks, Dick. So we've got time for some questions. So have you got any questions from the floor here? No, I think everyone's satisfied. Robert's got a question.
I'll ask about resilience for smoke and like air quality. Like I'm extending my house, renovating it. It's not going to be a passive technically, but I want to get it as airtight as possible. I started at 20 air changes per hour, hoping to get to single digits. And one of the things I need to do is get rid of the ceiling fan and put in a ducted range hood. And I was wondering about makeup air, and in looking into range hoods, I can actually get a makeup attachment to a range hood from Whisper. But I'm wondering if that's going to be sufficient or if there are other strategies. I don't think it's viable for me to do a ducted full centralized HRV type system, but I am thinking about maybe getting something on the wall, which is like a decentralized version.
Yeah.
But that would only have what comes in is equal to what goes out.
Yeah.
Whereas what I'm concerned about is if I run the range hood, I'm going to have a significant amount of air going out. And what confused me is Whisper is saying you don't need to have the same amount coming in from their gadget. Like they suck out about 1,000, 2,000 cubic meters per hour, but their makeup air unit is only about 550 cubic meters per hour.
Is that because they're assuming the house is so leaky that it'll just draw air from everywhere
I'm
else?
not sure. I've got to make another phone call to someone else to try and understand that. Because that's what surprised me. I don't understand that. So do you have any comment about makeup air?
Well, yeah. I mean, traditionally, makeup should always equal whatever's being drawn out in the first place. So, yeah, I'm with you on that one. It doesn't seem to make sense, and I'm assuming they're just working on the basis that most houses are leaky. But of course, that leakage will be bringing in unfiltered, uncontrolled air. In terms of your HRV issue, yes, fitting a centralised system in a retrofit it often just isn't practical, sadly. And you can get wall-mounted units in pairs. So in a room like this, which is about 80 square metres, 70 square metres, something, you'd have one over in that corner and one in that corner, diagonally opposite corners, and that would give you the best approximation of moving the air through the whole space. And they talk to each other by Wi-Fi. Is that me? Phew. And so one's sucking while the other's blowing, and then they, after several minutes, they reverse. And they have a little ceramic heat bank in them that acts as the kind of heat exchanger. It's an approximation, and they work reasonably well. They're certainly better than nothing, but you can't filter them down to anything even like PM10. They've got a sponge filter, and like it won't pull out smoke. Probably wouldn't even pull out dust.
And it wouldn't do any makeup actions either, because what comes in comes
Not
out.
for your. That's right. Not for your range hood. So it sounds to me like you almost need two makeup units to cope. Which is also then starting to sound a bit expensive. So the option, I guess, would be when you're running the range hood and external conditions outside are adverse, don't. Yeah. Yeah, sure. Yeah, well, that's right, because the makeup unit will be passive, I assume.
Apparently it's going to be quiet, so when the client's going to make the unit starts, the makeup
With a fan or just by opening?
fan.
Oh, right, okay. Yeah, okay.
So any other questions here? No, oh yeah, here we go.
Thanks for the presentation, Dick. I just wondered whether you'd be able to talk to the suitability of Australia's current building standards in the face of the changing climate and what you would think about, say, oversizing gutters and downpipes or upgrading roof fixings to cyclonic standards and that kind of resilience.
Okay. The current standard, which is not yet universally implemented around the country, is 7 stars in the NatHERS, using the NatHERS system. Passive house is a different system altogether. So trying to correlate passive house and NatHERS is difficult to do it exactly, but passive house isn't 10 star. It's probably 8.5, 9 star kind of equivalent, but it's up and down all over the place. So you can get a certified passive house design. When you run it through NatHERS, it'll come out at 6.5 star. And you go, gee, that's not real good. It's just because they're measuring different things in different ways. So the 7 star thing, which Western Australia, where are you? I'm looking at you here. Decided not to implement. Like, why? The cost of achieving 7 stars is very low compared to the benefit. Is 7 stars adequate to achieve real resilience and sustainability? No, it's not. Excuse me. But we were so frustrated with the recalcitrance of the couple of building industry associations who had been the loudest voice in the room and had been holding us back. You know, like go back to the mid-90s, and New South Wales was the first jurisdiction to introduce minimum thermal performance standards at 3.5 stars. And they cried, the sky is going to fall, you know, didn't fall. They increased that to 4 stars. Sky is going to fall, didn't fall. 5 stars, 6 stars. Every step along the way, they have fought tooth and nail to hold these standards back. And it sat at 6 stars for years. And we, you know, Renew had been advocating it for ages to have higher standards. Building Designers Association had been doing it. Institute of Architects had done it. Everybody with any kind of logical understanding of it, other than the immediate profit in this quarter for members, knew that it had to happen. So getting it to 7 stars, you know, why did is 7 stars adequate? No, but it was another line in the sand. It was like ratcheting it forward. Okay, we can't go backwards from that now. Oh, so, except in Western Australia. So we can't go backwards from that. The Territory didn't do it either, but the Territory is a bit special. Well, they're very special. Top end, yeah, okay. There are issues at the top end that are a bit unique. Alice Springs definitely should have gone with 7 stars, but Territory kind of went, no, we're different. So where we need to get to is probably 8.5 stars. At 8.5 stars, if you measure the thermal performance and heating and cooling energy used, you know, as your star rating goes up, it's going up and up and up. It's getting better and better and better. You get to about 8.5 stars and it starts to plateau off. Law of diminishing returns. So you don't need to be 10 stars to achieve net zero. You're going to do it at 8.5 stars, no problem. 8 stars even, you know, depending on the climate zone you're in. And then you throw on your PV and you throw on your battery and you've got a net zero building, a very, you know, almost fully autonomous net zero building. So that's where we need to get to. The 7 stars is not there. That's a staging post at best.
Well, there's a further question which follows on to that in terms of cyclonic fixings and stormwater. Comment from someone online who said that in far north Queensland and the NT, there obviously are built to cyclonic conditions, but we're now getting, like Brisbane's been hit with mini tornadoes and obviously the buildings aren't coping. I guess if I re-look at that, I mean, the standards for the cyclonic fixings is based on a map, which may need to be reassessed as to what areas should have those higher standards.
And I didn't address your question about gutters, I'm sorry, but that's hello, link straight into that one. That's right. So some of the rainfall events we saw last weekend in the Illawarra down the south coast of New South Wales were something like what you would see in a Cairns wet season, or, you know, Darwin, maybe not quite as extreme as a Darwin cyclonic rainfall event, but yeah, so those kinds of standards and the current standards are probably not adequate. One of the things, and I didn't put it in the slide deck, but one of the things we've been doing for some time is calculating the gutters to the Australian standard and then going, yeah, big half round ones are, you know, 40% more capacity than that, and they look better anyway, you know, so just upping it to the next big chunky size and downpipes go with it and so on. And that's where it then factors into what are you doing when you've got all that water off the roof, now what? You know, where's it go? Goes into tanks, great. When the tanks are full, when they overflow, where does that go? You know, so is the street infrastructure adequate, or, you know, do we need to do something? So a lot of councils have on-site detention requirements now, where you've got to hold a certain amount back and release it slowly to compensate for the fact that we've got so many hard surfaces and roofs and so on. And you know, there are ways and means of designing your tankage to get best value out of it. Don't have a standalone OSD system, because all that does is give community benefit, gives no benefit directly to the homeowner. But if you incorporate that into your domestic storage tankage, you kind of get that bit for free, and so that you drop the top bit of your tank to fulfill the OSD function, and you're storing the rest of it. So your tank's got to be a little bit bigger, but it's, the capital cost of that is much lower than building something standalone.
Discussion of gutters, and I remember being in Singapore where none of the houses had gutters
Yeah.
to prevent standing water, because all the 4 strains of dengue fever are rife through Singapore. Dengue fever is now working its way down the eastern seaboard of Australia. Is the tropical disease management coming into building standards?
No, it isn't. That's a good point, though. And a properly designed system and properly built system obviously won't allow standing water. But there's a maintenance issue there that I reckon if you did a survey of houses that are more than 10 years old, certainly more than 20 years old, you'd find gutters that are sagged and, a few things have gone wrong, and there'd be standing water. Yeah. Probably the difference between us and Singapore is that our evaporation rates are much higher. In summer, in the warmer conditions, when the dengue fever's at most risk, our evaporation rates are much higher. Singapore's constantly high humidity, means their evaporation rates are a bit lower, significantly lower. But yeah, look, I know, having spent some time in Singapore, and I've seen buildings that were designed, I think, badly, and there are some beautifully designed buildings in Singapore, but there was one in particular that had been designed very badly, with no eaves and no gutters, and it was just like this wall. It was 3 years old and it looked like it was 150 years old. It was terrible.
A friend of my house had the eaves, no gutters, but the rain came every afternoon, and he just got pulled.
Yeah.
But 60 centimeters out.
Yeah.
But it was every afternoon.
Yeah. And it's an interesting, this is getting off the topic, I guess, but Singapore are not having an easy ride with their freshwater supplies either. They have to do a lot of work to maintain their freshwater supply. You could argue that they should be harvesting a lot more than they currently are. I don't know. Anyway.
I've just got one question, which maybe we finish with. You talked about building design in bushfires in terms of standards and so forth. I guess that applies if you're renovating significantly or building new. What are some simple strategies for people who just have existing homes, and how to make them more resilient?
Yeah, that's a good question. It's a little bit like dominoes, once you start, where do you stop? And financial constraints, I guess, come into this as well. So the first thing to do is consider your risk. If your only real risk is just ember showers, then that's relatively easy to deal with. If you think you're going to start getting wind-blown debris and direct flame attack, that probably pushes you into the realm of starting to do things properly according to the standard. But if it's just ember showers, the things to do would be to have gutters that are either extremely easy to keep clean, or that have a very effective metal gutter guard, leaf guard over them. And the best kind of leaf guard is one that doesn't kick up, because then it just contains leaves and sticks, and they break down. You get all this detritus in the gutter anyway, and you still have to clean that out. So the best ones are where they literally either tuck under the second course of tiles and go straight to the edge of the gutter on slope, or if it's a metal roof, they conform to the metal but then go straight to the gutter, so that as sticks and leaf litter fall down the roof, they tend to go straight off the edge. Now, that will usually involve dropping your gutters, but so that's an expense. I mean, it doesn't mean you necessarily need new gutters, but it's still something that has to happen, probably, with a trade on site. So that's the first thing. And then to have some way of, in a bushfire event, filling those gutters full of water, which means that you have a little plug either at the top of a downpipe if you can get to it safely, or at the bottom of a downpipe if it's too high to do safely. And then you fill the gutters and downpipes with water so that as embers fall on your hopefully gap-free impervious roof, at least when they go down into the gutter, they're extinguished, because if they're not extinguished when it gets into the gutter, they can blow back up under the edge of your roofing and into the roof space, and then you've got real problems. Another thing that could be done is to just put an ember-proof seal on top of the fascia, which is usually a mineral fibre. It's like a rockwool insulation bat, but it's sort of in a strip, and because it's a little bit squishy, it'll conform to whatever your roof profile or roof tile profile is, and then have the roof put back down on top of those. That stops embers getting back up that way as well. It's still a good idea to have water in your gutters though, because typically your fascia will be timber, and there's often a little bit of fascia exposed between the top of the gutter and the roofing. Now, in a bell-rated design that you're doing from scratch, that fascia would be metal, so it wouldn't be an issue, and you'd have the ember proofing. So in that kind of roof, you don't need to worry about filling the gutters because there's nothing there to burn. There's no combustible material and there's no gaps. But if it's a retrofit, you have to assume there's a bit of timber exposed above the back of the gutter. So I think there's a question.
Fascia gutter. Don't use a fascia gutter.
Don't use a fascia gutter.
No. Higher than, than the roof.
Yes.
And they just
Yes.
do the opposite.
Yes, that's right. So a fascia gutter is a gutter. They're typically either square or they've got a bit of an angle, but the front face is way higher than the back, and they're designed to completely obscure the line of sight to the roofing, so that they started back in the late 60s. They first appeared, and they were very popular in the 70s and probably early 80s. Not so much now, but yes, that's impossible to get a leaf guard that doesn't kick up at the end if you've got a fascia gutter.
Okay. Well, that's been a very great presentation, Dick. There's so much to absorb. So thanks very much. And if we give Dick a hand.